All right, so moving on to geometric sequences, we're going to use what we know about exponential functions, and we're going to talk about sequence and finding patterns. So this is the geometric sequence. Geometric sequence is the ratio of any term to its preceding term is a constant value. So basically, our distance between the two terms is the same. Just remembering that ratios is a fraction. So a geometric sequence is a starting value A with a starting value A, and a common ratio R is a sequence of the form, and then here's the form A, comma, A to the R, comma, A to the R squared, comma, A to the R cubed, comma, dot, dot, dot. The pattern continues. So notice how our A and R stay the same, but our exponent changes. And so that's where this becomes an exponential function, like the way we figure this out. Now, a recursive definition of the sequence has two parts. We have to say what the first term is, so A sub 1 and what it equals, so we're going to call that A. So this is the initial condition. And then from there we can create what we call the recursive piece, which is A sub n equals A sub n minus 1 times R. And this is for any n that is greater than or equal to 2. But this is why we have to have A sub 1 already told to us so that we could plug that in to find A sub 2 and etc. And so then this piece here is what we call the recursive formula. And then an explicit definition is just one single formula. A sub n will equal A sub 1, our initial value, times R to the n minus 1. And this is for any n greater than or equal to 1. And every geometric sequence has a starting value and a common ratio. There's an A and an R. And the starting value and the common ratio define a unique geometric sequence. So we are able to write any, as long as we have the starting value and the common ratio, we can write any form of these, whether we're writing the recursive or the explicit, or we're just writing out the geometric sequence itself. So first things first, let's just decide of these three examples here, which are geometric sequences. So really, the way we figure this out is like here, I'm going to take 200 divided by 20. I have zeros that cancel out, and 2 divided by 2 is 1, so I end up with 10. So I know that here is just times 10. And if I look at it, I go from 2 zeros to 3 zeros, so again, I just took it times 10. And from 3 zeros to 4 zeros, so I took it times 10. And from 4 zeros to 5 zeros, so we took it times 10. This is, yes, it's a geometric sequence. Common ratio, I'm going to call that CR. Common ratio equals 10. All right, next one. If I do 4 divided by 2, I get 2, so this is times 2. But if I do 6 divided by 4, I get 3 halves. So this would be times 3 halves, or 1.5. And then if I do 8 divided by 6, I end up with 4/3. So this would be times 4/3. So if you notice, we're not multiplying by the same thing over and over again. So this is not geometric, and it's because there's no common ratio. Now, it is linear because we add 2 each time. But that's the difference between a linear function and a geometric or exponential function. Our linear function, we just have to add or subtract the same. Here, we're needing to multiply by that same ratio. All right, from 5 to -5, we multiplied by a -1. From -5 to 5, we multiplied by a -1. And then the pattern just keeps going. And so even though we didn't change the number, this is still geometric because we are still multiplying by the same number each time. And that's what makes it geometric. As simple as that. All right, so example 2, find the recursive and explicit formulas for the sequence 7, 21, 63, and 189. And so what we need is for recursive, we need a sub 1, which is our first one, which is 7. And then we can write a sub n equals, and then we have our a sub n minus 1 times our r. So then I need to fill that in. Here, I'm going to write that up. So we need what our a sub 1 equals, and then a sub n equals a sub n minus 1 times r. So we need to just figure out what r is. Well, 7 to 21 would be times 3. If I take this times 3, 21 times 3 is 63, and then 63 times 3 is 189. So our common ratio is 3. And that's the recursive. So this here gives us our recursive. That's all we have to do for recursive. You may be saying, Ms. Curry, that just seems way too easy. I promise you that's it. That is all. And what this means, this a sub n minus 1, if I'm looking for a sub 2, I'm going to take the fact that a sub 1 was 7, and I'm going to take 7 times 3. That's all that recursive formula means. All right, so now on to the explicit formula. So for the explicit formula, we needed the following. Explicit formula was a sub n equals, so this was recursive. This is explicit. All right, a sub n equals a sub 1 times r to the n minus 1. That's what we're working with. So from here, I know, so when I'm doing my explicit, I know that a sub n is going to equal a sub 1, which is 7, times r to the n minus 1. And that's it. That's our explicit form. There's nothing more to do. Now, with this explicit form, we can find it for any. For our recursive, we have to go through and find the term before it. So that's where explicit comes in handy. In the next video, we're going to do a real-world example using geometric sequence, and then writing it as a function and graphing it. So I'll see you there.